students. Oh, okay, we've got both teachers and students. Brilliant, because this is for teachers and students, just like it was advertised. This is working out so well. All right, we've got 30 people. It's 2 minutes past the hour. I think we should begin. So I was really debating how to handle this session. And I actually decided to go back to something that I very, very much believe in. So those that know me probably know exactly what I'm going to say today, but it's really an important message. One thing I really truly believe in is that there's no boundary between extracurricular mathematics and thinking and those sorts and schoolroom mathematics, because all mathematics can serve as a portal to joy and wonder and delight. You know, you might take the AMC, for example, and think this is all cool math. It's got nothing to do with my schooling or close, only barely related to my schooling. Or you can do a whole bunch of school math and not even think about competitions or other outreach work. I believe the two are entwined. So I really want to talk about the mindset of practicing problem solving, even with schoolroom mathematics. And the classic example that I really believe in, is that when I left the university world to become a high school teacher, I was really proud when I had to teach my students, the Algebra 1, a whole unit on quadratics, and I decided to make it not about the quadratic formula, not about memorizing this and that stuff, because I'm a mathematician. I really cannot memorize stuff. I can't even do arithmetic. I am lousy. But I'm so interested in the mindset of how do you garner the confidence just to nut your way through stuff and see if you can make some progress nonetheless. Be stuck, take a deep breath, and then do something. So today I thought I would just go through how I think about teaching a unit on quadratics. I'm going to do that, but I'm going to teach it in the way that we're really teaching problem solving as we go along, because I'm going to be absolutely honest. I don't think I've ever used the quadratic formula in my everyday life. I cannot think of any scenario when I was out shopping, when I was out trying to work out, I don't know, finances for refinancing a house or something like that, if I had to use the quadratic formula. I can't think of it. I'm a research mathematician. I actually did my PhD at Princeton, and I was doing high fluent research math. I don't think I ever used the quadratic formula then as well. So yeah, sure, the quadratic formula is beautiful and grand, but teaching quadratics is not about teaching the quadratic formula, actually. It's about the thinking mindset. So how do you teach the problem-solving mindset whilst teaching? And the best way to talk about it is to actually do it. So let me teach you about quadratics today. So if you're a teacher, great. If you're a student, great. This might be material you know so well already, but the point is to see how I'm turning it around. That's really the mathematics, that portal to joy, wonder, delight, and deep, powerful thinking. So here goes. Now, here comes Tanton fumbling with a screen. Share the screen. My individual application doesn't show up for reasons that don't make sense to me. Nope, it's not there. So I'm going to show you my entire screen. You'll get to see everything for a little while. Here goes until I sort out what I'm doing. Now you're seeing an infinite regress of me. How exciting. Many James Tans, infinity of them. Fabulous. But I need to share my document camera. All right, okay. I think right now I can see my screen. I can also see the chat. Can you guys see the screen well enough? Can someone give me a heads up in the chat whether this is good enough for you? Great. How many pens do you see? I'll believe you when you tell me how many pens you see. How many pens do you see on the screen right now? 4. Excellent. We're all good to go. Brilliant. Here goes. So let me teach quadratics. Let me illustrate what I mean by how to teach the problem-solving mindset whilst teaching. All right, but the thing is, first of all, as I said, I'm not really going to focus on the quadratic formula at all, nothing like that. I'll do it, of course I'll do it, it's a beautiful, good thing. But the story of quadratics, well, first of all, I just use the word story. So that's one thing, it's a story, it's a human story. There's human beings that did this stuff. Why do they do that? Well, they're human, they want to do it for human reasons. And it's really the story of symmetry, the power of symmetry. A course on quadratics is really a course on symmetry. So let me show you what I mean by that. Let me just show you the power of symmetry before we do anything about quadratics. For example, here's a silly little question, but it's a very potent question. I'm going to draw you a rectangle. Woohoo! There's a perfect rectangle. It is gorgeous, stunning, and absolutely on the mark as a rectangle. I will tell you that its area is 36 units squared. And then my question is, what can you tell me about the rectangle? Well, probably not much. You tell me it's a rectangle, because you told me it's a rectangle, James. You can tell me the area is 36, but you really couldn't tell much more. I mean, you might guess it's 4 by 9. Its dimensions are 4 feet by 9 feet. Or maybe it's 2 by 18, if I can do arithmetic. Or maybe it's, is it 4 by 9? Yes, maybe it's like, I don't know, 10 by 3.6. Who knows? You know nothing. You know very little. I'm going to say you really know nothing other than what I told you. You know nothing about that rectangle. Unless, I forgot to add one adjective. It's a symmetrical rectangle. And that's a bit silly because rectangles are symmetrical, but I mean it's the most symmetrical one of all. So I've got the most maximum amount of symmetry could possibly happen. As soon as I add the description, it's the most symmetrical rectangle you can think of, then suddenly your lack of knowledge completely collapses down to complete knowledge. If it's the most symmetrical rectangle of all, then you know it must be a square of area 36. And because you know it's a square, it's symmetrical, you know actually its dimensions are 6 by 6. So all uncertainty collapsed to absolute certainty with the mention of symmetry. As soon as I mention symmetry, we've got powerful, powerful knowledge at our hand. This is the story of quadratics. This is what the story of quadratics is all about. I'm teaching how to teach the problem-solving mindset and the human story of mathematics, even with school mathematics, and with the actual example. Great. So that's fun, because then I can actually have more fun. Before I can start what I'm meant to be teaching today, here's a classic question. A farmer, there always are farmers, I don't know why farmers are doing this. A farmer has 40 meters of fencing. She wants to make a rectangular pen of maximal area. This is such a school book problem, except you can actually read the school book. You can't actually read my handwriting here. Okay, so farmer has 40 meters of fencing. She wants to make a rectangular pen of maximal area. What dimensions? All right, so there's such a standard school book problem. It's so dreary. I don't believe farmers ever think this way. It's completely hokey, but maybe the mathematics is interesting. Well, the mathematics is interesting if you do the following. If we say symmetry is our friend, maybe I can focus answering this little question, this little made-up textbook question with the power of symmetry. So I'm going to say, okay, symmetry is my friend. Maybe I might guess the most symmetrical answer, the square, is the desired answer. But I know I'm likely to be off. I know it's not likely to be 10 meters by 10 meters by 10 meters by 10 meters. It might be 10 meters plus a little bit, 10 meters minus a little bit, plus a little bit, and minus a little bit. Maybe my rectangle is actually like that. In fact, I might as well start with the symmetrical case and actually play with this equation, this picture here, and say, how far off am I from symmetry? All right, so what would the area be? The area would be, if I wrote this rectangle this way, will be a 10 plus x by 10 minus x. So 10 plus x, length times width, 10 minus x, that's the formula of the area. And I quickly do my algebra, 10 times 10 is 100, minus 10x plus 10x, no x's, minus x squared. Bingo, so there's a lovely formula for the area. And right now, I know how to get my answer. What's the rectangular pen of maximal area? How do I make this formula the biggest? This is the biggest when x equals 0. Whoa, that is I have 10 plus 0, 10 minus 0, 10 plus 0, 10 minus 0. That is I have a square. Yes, the symmetrical answer was the optimal answer in this case. Symmetry is our friend. This is lovely. In fact, this is such a classic formula in classic problem in quadratics units and textbooks. I've done it now before I even started doing anything about quadratics. Whoa, crazy. In fact, it is such a human story. Let me keep going with the name. The name, quadratic. It is such a weird word. You should ask yourself, what on earth does quadratic mean? Where does it come from? We call any expression of the form ax squared plus bx plus c, we call it quadratic. That is weird, because if you think about it, the prefix quad is, well, 4. Quad means 4, like a quadrangle is a 4-angled figure. A quadrilateral is a 4-sided figure. So what's this got to do with the number 4? Do you have any thoughts? What's 4-ness in an expression like that? Why are people saying call these the 4 equations? Can you do your thoughts in the chat maybe? But if I get my camera to focus, there we go. It's weird. It's not at all obvious why this had anything to do with the number 4. Well, actually, if you think about it, it gets kind of weirder. Before I answer that question for you, look how we name equations. For example, if I got this equation, ax plus b equals 0, we call that a linear equation. And I guess that name makes perfectly good sense, because if I actually graph the equation of that form, y equals ax plus b, I guess I'm going to change my equation, you actually get a straight line graph. So people call these linear equations because they match how the graphs of the general expression maps as a picture. And then we have a x squared plus bx plus c equals 0. That would be called a quadratic equation, which is kind of weird. That's totally weird. That's what I'm asking about. So I want to know why that name. What's that got to do with 4ness? 4, huh? That's what I say. Then we have ax cubed plus bx squared plus cx plus d equals 0. What do we call those equations? Anyone know? Can you type in the chat what we call an equation like that? Cubic, yes, we call it cubic because we actually even say x cubed, so we call it cubic for 3ness. And then we have ax to the 4th plus bx cubed plus cx squared plus dx plus e equals 0. What do we call one like that? What do we call an equation like that? Quartic, which is curious, by the way, because quart is another Latin prefix for 4. We've gone to 4 again. And then the next one would be ax to the 5th, we call that quintic. Quintic means 5, quints from 5. Ax to the 6th and so on would be called hextic. I don't know. Maybe it's called hextic. Ax to the 7th, I'm going to have fun with this one. It might be called septic. That would be a septic equation. I think I've gone from Latin to Greek here. Uh-oh, I don't know why they call x to the 7th. But here's the thing. Look at this. This is weird. Linear, okay, sure, linear. But we go 4ness, 3ness for cubic, back to 4ness for cubic, then 5th, 6th, and 7thness. Our numbering is completely out of whack. These should be called to something to do with the number 2. Maybe we should call them two-tic equations or bitic equations, or what's another word? A die. Die is another prefix for 2. We should call them ditic equations, but we don't. We call them quadratic equations. Here's the reason. Here's the reason. It's this reason. It's the human story. People realize that quadratics are all about the power of a square, the symmetry of a square. People call them the equations that could be solved by using the power of a square. Now, the Latin word for square is quadrus. So people came to be known, call these equations as equations that could be solved by the square method, the quadrus method, which then eventually became quadratic in English. So it all comes from the original story about a course on quadratics is about the power of symmetry, about the power of a square. These became known as the equations that could be solved by the quadrus method. So they got their own special name because they came up 2,000, 3,000 years ago. People were doing this for a very long time, playing with these equations. Whoa, you've got to love the human story behind all this. The names are weird, and there's got to be something interesting behind weird names. So whenever you've got a weird word in your textbook, I say question it. There's probably some really curious story behind any weird word. This is brilliant and fabulous and wonderful. Love it, love it, love it. All very human, including the months of the year. It's very human. Yes. All right. Quadratic, because they're referring to those equations that can be solved by the quadrus method, by the square method. So now that I have just been rambling for 14 minutes about why I even want to talk about quadratics of the course, it's because it's a wonderful human story. Let's now do it. Let's now actually pretend I'm a high school teacher again in my life, teaching a unit on quadratics. Let's do it. I know you know the stuff, but the point is to see how you can really use this standard material as an opportunity to teach the mindset of problem solving. So I'm going to solve the algebra of quadratics like a video game. I'm going to have different levels. Here is a level 1 equation. I'll go through level 1, level 2, whoops, you can see it, level 3, level 4, level 1 quadratic. So what I'm going to do now is this. I'm going to say, please solve this equation, x squared equals 16. And I know I'm insulting your intelligence, but the point is not about actually doing the question. It's about the thinking and the mindset and the brain power behind this. This is really grand. Here goes. I've actually given a major clue in this question. We call this x squared. We actually even literally say the word square. People seem to forget that our algebra is full of geometry language. X squared is 16. X as a square is 16. So actually, I use a geometry word. I can draw a picture. Let me draw a picture of what we literally said, x squared. X as a square, and x by x squared has area 16. So I'm back to the very first thing I did. And right away you say, oh, well, James, I know exactly what x has to be. It's a nice symmetrical square. X must be 4. Bingo, bingo. Now, if you keep your mindset purely in terms of geometry, yes, x will be 4, that positive length 4. But actually, if you open up your mind a little bit, this picture actually has another solution to it that doesn't quite make sense for geometry, but actually makes sense in arithmetic. 4 times 4 is 16, yes. Or x could be -4, because in arithmetic, -4 times -4 equals 16. Doesn't make sense in geometry here, but this picture is still representing the same arithmetic truth if I go with the negative answer there. So technically in arithmetic, there's two answers, which I can see kind of both of them by drawing a picture. Great, great. Let me tell you this one more time. Let's now solve x squared equals 100. And just to really press the point, I just literally said x squared. Let me draw a square. Beautiful. Just do what I literally said. X as a square has area 100. And I know it has to be 10. X must be 10 if I'm thinking pure geometry. Or if I open my mind a little bit and say it could also be the negative version of that, great. There is level 1. Now, of course, there's some little issues with level 1. For example, I could ask you to solve x squared equals 0, which doesn't quite make much sense in geometry, or maybe it does. I mean, a square of side length x has no area. So let me draw a picture of that. Probably can't even see that. There it is. So what must the side length be? X must be 0. It must be 0 by 0 square. Or maybe x equals negative 0. Ooh, this then leads into a deep question. Are these the same? Oh, already I'm in a puzzle. Is negative 0 the same as positive 0? I know I was told they were as a kid. And when I was a student, we said, no, negative 0 is the same as 0. We just said it is. It is. I want to know, if you think they are the same, why? Well, there's a good puzzle right now. Oh, before we get to level 2, there's actually something quite deep to play with. Okay, great. This is a portal to mystery, wonder, and delight. Even here, level 1 quadratics. In fact, even now, x squared equals negative 5. I try to solve that one. Now we're getting to deeper territory. Can some number times itself be a negative answer? No, because positive times positive is positive, and negative times negative is positive. You'll never see a negative answer. Really? How do we know negative times negative is positive? It's one of those things I've been told all my life since grade 4 or grade 5, back for me in Australia, that negative is positive, because it just is. I never was told why. Never even explored why in the class. For my schooling, another deep mystery naturally comes up. So even though I'm in high school now, it doesn't matter. These are deep mysteries that should be explored and thought about. If no one thought about it, gave you good reason to understand these things, now's a good time to try to understand these things for yourself. They're very deep. Anyhow, my point is, level 1. A square has a certain area. You can literally draw a picture. There's the quadris method, the square method, right before our eyes, showing you what to do. You get the actual geometry answer. And if you open up your mind just a little bit, you also get the arithmetic answer as well. That matches the picture, even though the picture doesn't have negative side lengths in geometry, still it's speaking truth in arithmetic. All right, I think we're ready for level 2. Level 2 quadratics. This is so fun. Okay, level 2. There's only 17 levels. That's all, don't worry. And we've only got 41 minutes left together. No, 31 minutes left together. All right, let's get through all 17 levels. Well, let's go up a notch in difficulty. Level 2 is up a notch. Let's solve x plus 3 squared equals 16. Whoa, scary. Well, maybe it's not scary. So, all right, how it goes. What are we going to do here? Well, we said the word square again. Something squared is 16. So literally, this is something squared is 16. So my something, when I use it as a side length of the square, gives an area of 16. And what's my something? Oh, it's x plus 3, or x plus 3. So something squared is 16. My something better be 4 or negative 4, just like I was doing in level 1. Something squared is 16. My something is either 4, or my something is the other version of arithmetic, negative 4. Bingo. That's just following level 1. Done. Except most people say, no, you need to tell me what x actually is, James. You can't just leave it at that. Okay, I'll go the extra step. Let's subtract 3 from both sides, x is 1, or subtract 3 from both sides, x is negative 7. Bingo. So basically, it's just still a level 1 problem. Just my something was a bit weirder this time. Great. All right, your turn. Here's a level 1, just for fun. Can you please solve for me 2x plus 4 squared equals 81? This would freak out many young students doing this for the first time, but is it worth being freaked out about? What answers do you get? I'm curious. Just a quickie. Yeah, it's really just level 1. Something squared is 81. So my something is either 9. My something is either 9 or the negative version, if I'm going to go full arithmetic. Bingo. And now it's just a little bit of algebra. Subtract 4 from everything. So 2x is 5, or 2x is negative 13. X is 5/2, or x, or I'm off the page. X is 5/2, or x is negative 13/2, which I think people are typing. Beautiful, beautiful. Level 1, piece of cake. Level 1 done. Level 2 done. I think we're ready for level 3. But let me just insult our intelligence one more time by, let me do this level 2 problem one time. Here it is. If I was given that one, I say, well, that's just something squared is 25. The picture is obvious, James. You just draw something, an area of 25 with something being x plus 3 this time. I can see right away x plus 3 better be 5, or x plus 3 is the negative version of that, which so gives me x is 2, or x is negative 8. I think I've done that correctly, but who knows? I cannot actually do arithmetic with confidence. All right, great. All right, that was level 2, piece of cake. Here comes level 3. By the way, it's not really 17 levels. Don't panic. Don't panic. All right, okay, level 3. Let's solve x squared plus 6x plus 9 equals 25. This is where I loved being a high school teacher teaching quadratics. I actually love teaching this stuff, not because I think this material per se is exciting in terms of actual solving equations. If I really need the solution to that, I'd probably type into Wolfram Alpha or something like that if I really wanted the answer. But the goal is not about getting the answer. The goal is about the thinking here, the deep thinking, how to teach the problem-solving mindset whilst teaching standard school mathematics. And the thing to realize is, when you see this for the first time, imagine being a student again, imagine being back to your young self. When you're doing things like this, you said, no worries, piece of cake, you suddenly get to this. This is visually horrible. This is totally horrible. Ick, ick, ick. My emotional reaction is horrible. This has suddenly gone up a notch difficult. This is visually very scary. I'm scared. That's my emotional reaction. All right, so take a deep breath. That's okay. It's okay to be human. It's okay to have an emotional reaction. It's always good to acknowledge your emotions. Take a deep breath and see if you can do something nonetheless. And the thing that I notice, we're still talking about squares. I still say square here. I've still got symmetry going on. So I can at least draw a picture of x squared. I can at least draw an x squared piece. There's an x squared piece which comes from x times x. I can at least draw that much of the picture. Great. But the thing is, there's more to this equation. So what could I possibly do? And this is where it becomes a problem-solving strategy. There's x squared, got it, but there's more to it. How could I possibly add to this picture a piece of area 6x? All right, so now I'm actually engaged in problem solving. What can I do? Well, let's try something. Well, 6x, I've already got a side of x. What if I put a side of 6 here? That'd be really nice. That would give me a piece of area 6x. That'd be lovely, actually. 6x. 6x would be 6, times x. There it is. There's a piece of area 6x. Great. And got that. So good. I've got 2 pieces. Then I've got to add a piece of area 9 to this picture. But also, actually, right now, I'm getting really nervous. This is actually making me feel queasy. So I've got, my emotion right now is queasiness. Because look what I've done here. That's a square. I've kind of deviated from symmetry. I've actually made like an oblong here, which is very not square. Putting 6x this way was kind of unsymmetrical. So now I'm double guessing myself. Is there a way I could actually add an area of 6x by somehow keeping this picture symmetrical? Don't deviate from pictures that are symmetrical. I like squares. Right now I've gone away from square. And this is a problem-solving moment. Takes a while. As a teacher, I could just tell my students to do this, but no, as a teacher, we can get stuck on this till someone has the bright idea to do the following. You could actually put half of the 6x over here, so make it just 3 wide and x wide, so there's 3x. Put the other half of the 6x down there, trying to keep the picture symmetrical. X times 3, 3x. X times 3, 3x. And now I've got 6x again, but it's now symmetrical. Now symmetrical, which is beautiful because it now seems irresistible to complete this picture of the square. It seems so compelling to want to do that. And what's the area of that extra piece? It's 3 by 3 is 9, which lo and behold is the extra part. This is crazy. By keeping my picture symmetrical, the x squared piece, then adding the 6x symmetrically, breaking it into 2 even parts, and then I lucked out and had a 9 here, I can see that this question is really a level 2 question in disguise. The power of problem solving right now in this course on quadratics, which is amazing. In fact, I can see right now, this is really an x plus 3 by x plus 3. X plus 3 as a square has to be 25. All this is really x plus 3 as a square and must equal 25, in which case it really was my previous problem, which I've already solved, in disguise. This is the challenge of level 3. Can you recognize a scary looking thing as really a level 2 problem in disguise? What power? The power of going for symmetry. In fact, people even call this technique completing the square because guess what we're doing? We're literally completing the picture of a square. It actually makes sense. That name actually has a reason to it. So let's try this one. On your own Z's, quickly solve for me x squared minus 2x plus 4 equals 81. But do so by drawing a picture that's as symmetrical as you can make it as you go along and literally complete the square in your picture. I'll give you just a moment or two to try it. Give it a try, see what happens. Oh, that's a bad one. I think I just did a bad one. That is a bad one. Oh, that's okay. We'll go with that. Oh, no. I really am being bad. Sorry. X squared minus 2x plus, because I can't do arithmetic in my head. Try that one. I'm sorry, guys. Silly me. James Tanton cannot do arithmetic. For beans. Because his pen is running out. I'm doing it too. I'm being silent. This picture is just relying on arithmetic. The picture doesn't make much sense in geometry with negative side lengths, but in terms of arithmetic, it's still speaking truth. And negative 1 to negative 1 is plus 1, which is exactly what I want. So this was really x minus 1 as a square is 81. Beautiful. It's level 2. X minus 1 is 9, or x minus 1 is negative 9. So x is 10 or negative 8. Beautiful, beautiful, beautiful. You've got to love level 3. It's just level 2 in disguise. This is grand and good. In fact, I was actually jumping ahead of myself. Let's keep going. Let's go to level 4. Let's just boldly move forward in this how to use school mathematics as a portable teaching problem-solving strategies. Level 4, how to teach the problem-solving mindset whilst teaching standard curriculum material. Let's try this problem. Let's try this one. My brain was kind of going there before. Let's do something awkward like x squared minus 4x plus 3 equals 15. Because here's the thing to do with students. Just keep giving problems. I don't mean more exercises. Actually supply examples that have challenges to them that are problematic. This one is now problematic. There's a trouble with this one. What's the trouble with this one? What don't you like about this one when you try it out? It's a level 4 problem. What goes wrong? What goes awry? This one is failing in its symmetry. You are absolutely right. The plus 3 doesn't something. It just doesn't. It doesn't work. That plus 3 is annoying. That is annoying. Bother. Oh, we have a challenge. Houston, we have a problem. So let me draw it out. Let me draw it. So I know I'm going to try to make a big perfect symmetrical square. So I might as well just draw the 4 pieces right now. One of the pieces is going to be x squared coming from x times x. Got my symmetry. So far, so good. Symmetry. Keep it symmetrical, split it into 2 equal parts. Okay, there's my negative 4x. Got it. X times negative 2 will make the negative 2x. X times negative 2 makes the 2x. Beautiful. Definitely got everything there so far. Which means the remaining piece I want is negative 2 times negative 2 is 4. 4. Uh-oh. 4. We have a mismatch. We have a mismatch. The problem wants a 3, and we've got a 4. Uh-oh. Panic, panic, panic. I'm feeling sad. I've got ears for some reason. I don't know why I have ears. Okay, I'm a sad kitty. I don't understand what to do. We've got a problem. Teaching the problem-solving mindset whilst teaching. So now we have a problem. What could I possibly do right now? Oh, any thoughts? Any thoughts what we could do right now? Or should we just give up and go home? Well, that's a good strategy. Here's a great strategy in problem solving in mathematics and in life. If there's something you like, there's something in life you want to make happen, make it happen. And as Georgina's saying, deal with the consequences. I want a 4. I don't have a 4. Then I say, make a 4 happen. Turn that 3 into a 4. And how do I turn that 3 into 4? By adding 1. If I add 1 to the left, there are consequences. I can't just willy-nilly add 1 to the left. I better go and add 1 to the right as well. In which case, I want to rewrite this as x squared minus 4x plus 4 equals, 16 now. Now, why do I bother doing that? Why do I like that so much? Well, that x squared minus the 4x plus the 4 is precisely this square. X minus 2 as a square is 16. Bingo, we're back to level 2. My something better be 4, or my something better be negative 4. So x better be 6, or x better be negative 2. Bingo, we brought it back to level 2. If there's something in life you want, make it happen. Deal with the consequences. What a great problem-solving strategy right there. Absolutely beautiful. There is level 4. Grand, grand, grand. Okay, do you want to try one on your own, Z's? Yeah, try this one. Try this one as by drawing a picture and following the life principle. If there's something you want to make happen, make it happen. 10x plus 12 equals 0. Try solving that one. Set. I need my camera to stay in focus. Let's go on your right. We can't go home because we're all home. Mentally go home. All right, I'll try it too. I'll be semi-silent about it. Oh, might as well just draw the whole picture right off the bat because I know I'm going for symmetry. I think I want to add 13. If I do it on the left, I better do it on the right as well. I think the numbers are awkward, but in principle, the idea is straightforward. Why do I want that 25 there? Because then I can see that x squared plus 10x plus 25 really is x plus 5. X plus 5 as a square is area 13. So something squared is 13. That's not a nice number with respect to square roots. Oh well. So x plus 5 will be the square root of 13, whatever that number is, or it could be the negative version of that, negative root 13. Bingo. Bingo. And to get x all by itself, so x is root 13, take away 5, oops, or x is negative root 13, so to cut right, take away another 5. Messy, 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 but the idea is straightforward. Turns out there's an awkward square root number there. Oh well, that happens in life. Not a big deal. All right, levels 1, 2, 3. 1, 2, 3, and 4, all done. I think we're now ready for level 5. Let's start really practicing our problem-solving strategies with another problem in the quadratic equations I'm giving you. Let's solve x squared plus 3x plus 1 equals 5. Give that a quick little try and tell me what you like or don't like about that example. Three is not even. You're right. If we actually try to draw the square method, the quadrus method, why these things are called quadratic equations, X squared, x times x, absolutely. 3x has to get split into two even symmetrical parts. 1.5x, 1.5x. My brain thinks fractions. I think other people's brains thinks decimal. Either way, you're in decimals or fractions land. 1.5, 1.5. This piece must be 1.5 times 1.5 is, I just go yick. It's just getting yicky. It's yicky. That being odd equals ickiness. Now, I could do it. I could keep battling my way through this, and it will not let you down. This method will work, but I'm dealing with decimals and fractions. So here's our challenge. This is what I mean. Teach the problem-solving mindset whilst teaching school mathematics. What could we do if we don't want to get into fractions and decimals? What could we possibly do to solve this issue about this middle number being odd? Any thoughts on what we could possibly do to get ourselves out of this ickiness? Any ideas? Any brilliant ideas? Oh, can we make an odd number even? Just double it. I love it. Let's double everything. Oh, that is great. That is brilliant. Let's just double everything, times everything by 2. So let's make it 2x squareds plus 6x's plus 2 equals 10. I love it. Bingo. 6x, nice and even. We split them in half. So here goes. So let me draw my symmetrical square. 2x squareds. How do you want to split that one up? What times what equals 2x squareds? Well, if I'm going to keep symmetrical, I have to do root 2x by root 2x. Root 2x times root 2x would be 2x squareds. I could keep going. This will work. I have a feeling if I didn't like fractions, didn't like working with fractions, I'm sure not going to like working with square roots. So, excuse me, that's kind of made it worse or differently bad or something. That's kind of awkward. That is awkward. But you know what? Actually, it's a fun challenge. Do the quadratic method with fractions. You'll get an answer. Just battle your way through it. It'll work. Then try this quadratic method with the square roots. It will work. We'll give you the same answers. But most people don't like doing either of those things. And someone just had this brilliant move in the chat. This is inspired. This is one of these things that just takes, I don't know what makes you think of it. It's like you have to go for a walk and not think about this problem for an hour. Then instead of multiplying by 2, you might think what someone said in the chat, multiply by 4 instead, which seems crazy, but let me do it. See, we've got ourselves some space here. Let's take our equations and multiply everything by 4 instead. 4x squareds plus 12x's plus 4 equals 20. All right, I've just made the problem what looks like crazy bigger. Why? Well, because someone suggested it. Because look at this. Look at this. I can draw the square for this one and not get into decimals and not get into square roots. 4x squareds. That's nice. That's a perfect square. 2x times 2x makes 4x squareds. Loving it. 12x, let's split symmetrically. I can do it and still saying whole numbers, 6x and 6x. Love it. This is so far so good. Got that piece. Got that piece. Let me keep going. Something times 2x makes 6x. This better be 3. Something times 2x makes 6. This better be 3. All right, which means the final piece for completing the square, literally completing the picture of the square, 3 times 3 is 9. Oh, no, bother. We've got a mismatch. We've only got 4, not 9. What can I do? Yes, we're not fazed by that anymore. If you want 9, make it happen. Do all the consequences. So really, this is 4x squared plus 12x plus 9 equals 25. And why did I bother doing all this crazy work and turn it into that? Because that 4x squared and 12x and 9 is precisely 2x plus 3 as a square is area 25. And I'm back to level 2. I won't bother solving it right now, but we can keep solving that. Bingo. Everything is level 2 in disguise. You've got to love this. Welcome to the art of problem solving. Bring everything back to a simpler problem. I bring everything back to level 2. I love it. Draw a picture is a great problem solving strategy. I'm doing that right now. I'm teaching all the standard problem solving strategies for AMC work or for just mathematics in general. This is great. This is fun. I'm having fun. In fact, on your ownsies, try this one. Try solving x squared plus x equals 3/4. If you like fractions, go for it. If you don't like fractions, maybe do something about it. Give it a try. Draw me a beautiful picture of a square, literally a picture of a square. Complete the picture of the square, literally, and solve this equation. So I have a feeling multiplying by 4 is going to be doubly good this time, because I'll get rid of the oddness there. That's annoying. So that will fix that problem. And also we have 3/4. Multiplied by 4 will actually get rid of the fraction we're dealing with in the equation. So maybe playing with 4x squared plus 4x equals 3 is particularly nice. I wonder if I can draw a nice symmetrical square on that one. Yeah, it's a level 2 problem on the side. Brilliant. Anyone actually solve it? Anyone get the actual numbers? I'm just curious. Anyone actually got the actual numbers? What solves this thing? Is it a half and negative 3 halves? I'll believe you. I'm not the arithmetic. But the thing is, this is brilliant problem solving. Take a problem that looks icky and reduce it to something you know how to do. Bring it back to level 2. Okay, all right, here goes. I said there were 17 levels. I'm lying. There's only 6 levels. 1 more level to go. Let's do it right now. This is going to be an example that has everything that could possibly go wrong, but this example does go wrong. Can we use our problem-solving confidence to deal with this level 6 problem? This is the final level. This is as hard as it gets. Please solve 3x squared plus 5x plus 1 equals 9. And you might have noticed now there's something I've been carefully avoiding all this time. I've never put a number in front of the x squareds until now. So we've got a problem. There's a number in front of the x squareds. I've also got a problem that I've got an odd number in the middle. And I've also bet things aren't going to match up. Everything that can go wrong goes wrong with this example. So what could we possibly do to handle this? Any thoughts? Whoa, someone's being way clever. Someone's being way, way clever. All right. My brain is very slow. I'm a very slow fellow. So, okay, we've got 3x squares right now, which I have a feeling is awkward. That's going to get us in square root land. Root 3x. I don't want to do that. I could do it. I bet it will work. Okay, but is there any way I can keep myself out of square root land? And my first thought, because I'm slow, is like, if I want to deal with that 3 and make it nicer, what if I multiply by another 3? Multiply everything by 3, because that will turn that into 3 times 3, which is 9. 9x squared would be fine. It's a perfect square. So I make the first one a perfect square, life will be good, at least for the first term. Times 3 is 9x squared, plus 15x's, plus 3 equals 27. Great. So now I've got 9x squared here, and make that 3x and 3x. Looking good. Except 9x squared done. Beautiful. Oh, I've got that odd problem right now. I've got an odd number in the middle. So as we said earlier, maybe the trick there is to multiply by 4. So multiply by 3 and then multiply by 4. So now I've got 36x squared plus 60x's plus 12 is, 54, 108. James, you're being crazy by making this problem even bigger. These numbers are insane. So it looks like I'm multiplying by 3 and then multiplying by 4, which is the same effect as multiplying by 12, which is what some people said in the chat. So I'm doing the same thing that people said in the chat. Question is, does it help? It's a brilliant idea maybe, but that's fine. As we've seen, many brilliant ideas are brilliant, but just turn out not to be helpful, alas. 36x squared. Oh, multiplying by 4 has not ruined our perfect square. We've still got a perfect square. So 6x and 6x. Beautiful. 60x, that's even. 30x and 30x. Oh, this is good. Got that? Got that. This is so far so good. Something times 6x makes that 30x. It must be a 5 there. Must be a 5 there. Okay, it must be a 5 there. Great. Which means the piece I want is 25. Of course we have a mismatch. We know we're going to have a mismatch. Every problem that can happen is happening. Okay, but we're not phased. If you've got a mismatch, don't worry. Make it happen. Make that 25 by adding 13. Deal with the consequences. If you're adding 13 on the left, you better add 13 on the right. So what have we made this crazy problem into? We made it into 36x squareds plus 60x's plus 25. I'm cramming this onto the page equals, oh, arithmetic, oh no. 108 plus 13 is like, 8 and 13 is like a 21, 121. So like 121, I believe it is 121. Oh, that's suspiciously nice. 121 is 11 squared. In fact, this is why I bothered doing all this work. I can now see it's level 2 in disguise. 36x squareds plus 60x's plus 25 is really 6x plus 5 as a square. 6x plus 5 as a square is 121. It's level 2. 6x plus 5 is either 11 or 6x plus 5 is negative 11, and then I can keep going. I don't feel like keeping going. Brilliant, brilliant, brilliant. Okay, I love it. If your front number is weird, you can always multiply by another copy of it to get a perfect square for yourself. If your middle number is odd, you can always multiply by 4 to deal with the oddness there. If you've got a mismatch, don't worry, you can always deal with the mismatch. Everything falls into place. For the remaining 2 minutes, I'll tell you, I've been doing the quadratic formula in disguise all along. This is the quadratic formula. This quadris method is the quadratic formula. I like this method because I can see what I'm doing, and I'm really speaking to the story of symmetry, the power of symmetry. Mathematicians love symmetry. I'm using the symmetry of the square to solve these problems, bring it all back to level 2. But if you're wondering, James, where's the quadratic formula? It's what my school's meant me to do, makes me do. Here's the quadratic formula. So, for starters, I never bothered about changing the last number because I know I was going to change things in any case at some point. So if I didn't have 0 at the end, I didn't bother about that because I knew I was going to change it later on as I kept going. So I just kept it as it was to the end. But the school books want you to always make equal to 0, which is annoying. Okay, if that's what they want, that's what they want. So books insist, make it equal to 0. You don't have to, but okay, that's what I'm insisting. Now, let me use exactly the box method to solve this equation. What I'm going to do on the page is going to look scary because I'm going to do pure abstract algebra here. However, I'm going to use exactly the method we did. The fact is, this might not be a perfect square. So to cover myself, I'm going to multiply by a to make it a perfect square. So I'm going to make this a squared x squared plus abx plus ac equals a times 0. 0. Come on, don't be out of focus now. This is a key moment. All right. Now, I don't know about AB. It could be an odd number. Just to cover myself, I'll do the same trick again, multiply by 4. So let me play with 4a squared x squared plus 4abx plus 4ac equals 4 times 0. So let me play with this equation instead. Let's do the 2 fixes that came up earlier on. Let's play with that one that should fix everything for me. Let me now try to draw the square method on this version. This is going to be crazy. I'm now running out of time. Okay, here goes. Literally completing the square, the quadris method. 4a squared x squared. Yes, that's a perfect square. I can see it's 2ax and 2ax. In fact, I can see multiplying by 4 will never get me out of integers. This is still fine. That's great. Got that piece. 4abx must be half of those 2abx. 2abx. Bingo. Split into 2 symmetrical parts. Something times 2ax is 2abx. Oh, b times 2ax is 2abx. b times 2ax is 2abx. Which means the piece I want here is b times b. b squared. I don't have it. I have 4ac. All right, let's make it b squared. Let me get rid of the 4ac. Let's subtract from both sides. And let me add in a b squared on both sides. Because now we're cooking. 4a squared x squared plus 4abx plus just a single b squared equals a b squared to take away 4ac. Well, that sounds awfully suspicious. B squared minus 4ac. All right, why did I bother going through all that horrible work? Because I recognize this as my perfect square. It's my 2ax plus b as a square. 2ax plus b as a square is b squared minus 4ac. Oh, it's level 2. Everything is level 2. Bingo. So 2ax plus b is either square root of b squared minus 4ac, or, let's go on the page, 2ax plus b is the negative version of that. I'm just copying my method. I'm not doing anything clever. My brain is not clever. I can only do things I've done before. I'm a very slow thinker, I am. But if I want to get x all by itself, oh, how am I going to do this? We're running out of page space. So let's go from here. Let's go to this one. And maybe I'll do a different color so it stands out because I'm running out of pens. My pen's drying up. All right, so let's subtract b from both sides. Now, for some reason, school books like to put the negative b on the left and the negative b on the right, but they always put the negative b first. I'm not really sure why, but they do. All right, I can do that too. Negative b plus the square root of b squared minus 4ac. All right, that's one. And the other one would be 2ax is put the negative b in the front. Negative b, take away the square root of b squared minus 4ac. Great. And to get x all by itself, let's divide by 2a. So x is either negative b plus the square root of b squared minus 4ac all over 2a, or x is negative b minus the square root of b squared minus 4ac all over 2a. Whoa, whoa, no need to memorize that, actually, because it's exactly that picture. This picture is the standard quadratic formula. That's brilliant, that's amazing. This is why these things are called quadratic equations. Just draw the picture of a square. The Latin of the square is quadrus, the quadrus method. The method we solve by the power of the symmetry of the square. And this is why I love teaching so much to school mathematics, because each subject is actually that portal to teaching powerful, powerful problem-solving thinking, which is good not only for maths and any other problems you want to do in maths, but also many problems you want to do in life. The confidence just to try something and nut your way through stuff. Just keep trying, keep flailing. We made mistakes along the way. Well, there's not mistakes. We made learnings along the way. For example, doubling was a brilliant idea. It turns out timesing 4 was even better. That's actually technically helpful. It's going to happen. Flailing and fumbling. What a beautiful, beautiful thing. So on that note, I'm going to stop sharing my screen so I can see you a bit better. Except I can't see you at all right now. Right there. Oh, my hair's gone all funny. And say, thank you, thank you, thank you. If you Google, actually, let's see, where do I have this? I've got videos of me doing all this quadratic stuff and way more on quadratics and many other things. If you just Google my YouTube channel, James Tanton, I think I've got a series of videos that go through all the quadratics. Plus, I've got so much stuff written up everywhere. So if this is very fast, well, it was very fast, you can easily find online. If you can't find it online, let me know and I will send you gobs of stuff. My email is easy to find. So on that note, I'm going to say thank you, thank you, thank you for coming along. Just a little illustration how mathematics, all of it is actually a beautiful, beautiful journey into mystery, delight, and awe. So thank you so much, everyone. And be well. Have a good rest of the weekend.